So in that sense, the system spontaneously breaks the symmetry. Interaction, the Hamiltonian itself doesn't have a special direction. Right? The only thing in the Hamiltonian is the fact that the magnetic dipole moments, nearest neighbor magnetic dipole moments, want to be in the same direction. But that direction doesn't have to be any special direction. But in order for magnetic moments to all line up as you lower the temperature, below this temperature, magnetization shows up. That means they're not pointing into all possible directions, but they're all somehow point in the same direction. Right? That direction is chosen by the system by itself. Sometimes it's this way, sometimes that way, sometimes it's this way. So in that sense, the Hamiltonian itself has no special direction. It has a symmetry. Right? But the actual state, wave function of the system breaks the symmetry. Magnetic moments decide themselves, okay, this is a special direction today. Okay? So in that sense, this is, as the magnetization shows up, the symmetry is broken. It's called spontaneously broken symmetry. Okay? And the important point is the Hamiltonian doesn't have any special direction. Okay? Therefore, this special direction can be any direction, but it has to be one direction. Okay. Now, this is a result of the mean field approximation. And if you compare the behavior around here with the exact results, then you will see that it's different. Mean field approximation doesn't give you a right result. And if you look at the behavior around here, it's also wrong. Okay? But the qualitatively increases, and also the fact that there's a special temperature, Curie temperature, at which spontaneous magnetization shows up, which within the mean field approximation is the same as theta. But if you do exact calculation, or in a real material, so if you do either exact calculation or if you do experiment, then T sub C, Curie temperature, below which the magnetization shows up due to the interaction, is usually lower than theta. And you can show if the system is two-dimensional, then T sub C is 0. Okay? Whereas theta is not 0. Therefore, mean field approximation. I told you the mean field approximation is pretty bad in 2 dimensions. And here you can see one of the manifestations, one example that the mean field approximation is bad in 2 dimensions. In 1 dimension, and this is not ordered, even a T dimension. 1 dimension, of course, even at T equals 0, there's no spontaneous magnetization. Okay? So the mean field approximation is kind of okay at 3 dimensions, although these 2 temperatures turn out to be the same and the temperature dependencies are not exactly right. But in 2 dimensions and 1 dimension, mean field approximation is really bad. Okay. How much time do I have? I have 6 minutes. Okay, so I thought I can talk about the antiferromagnets, but let's postpone that to next week. And I'm going to talk about heat capacity or specific heat, as well as the magnetization of the antiferromagnet when J equals negative. And let me just add a few things. Something which you have to do numerically. This is all a low temperatures in zero magnetic field. You may ask what happens in magnetic field when the magnetic field is not 0. By the way, I decided in this trip, I came to Japan 2 weeks ago, which I don't do very often. Last time when I was in Japan was 4 years ago, so there was a conference to which I came. So this is one of the few opportunities. So I've been preaching at the various universities where I've been asked to give a talk. If you read the paper on magnetism written by either a Japanese people or German people, then you see that something is done under a magnetic field. Okay? This is German or Japanese. This is not English. In English, of course, you say in a magnetic field, right? Under is used under condition or under pressure. Okay? For such nouns, use the preposition, not preposition, what is that called? A preposition? Under. Okay? But when something is placed in magnetic field, field is, right, you're in a field. Right? You walk in a rice field, so in a magnetic field. Right? And another thing I've been telling people, if you plot the magnetization as a function of, sometimes people use H field, because H field is the field you apply from outside. Or sometimes people use the B field. This is a total field, including the magnetization. And you have a curve. As you raise the magnetic field and your material is antiferromagnet, then when the field is 0, even in the ordering, below the ordering temperature, there's no total magnetization, as you will see next week, or you know already. But as you apply the magnetic field, magnetization will evolve, and then eventually all the magnetic moments are pointing in the same direction because the magnetic field is very, very strong. Such a curve, mostly Japanese authors call magnetization process. Okay, and there's even a Japanese word, which I didn't know when I was a graduate student, therefore I think it's a translation of this wrong English. There's even a Japanese which corresponds to this English. Okay? But there's no such words. A curve can illustrate the magnetization process, right? Because the misunderstanding comes from the fact that the word magnetization has two meanings. One is this physical quantity M, which is a magnetization, but also magnetization is the process of magnetizing, right? If you magnetize something, that procedure or process is called magnetization. So magnetization process, these words means the process in which the magnetization material is magnetized. The process in which the material is magnetized. Okay? And such a curve, of course, this is a magnetization curve in correct English. This curve illustrates how the magnetization evolves, how the material is magnetized, right? That's why there are papers in which such a curve is used to illustrate the magnetization process. You may see an expression written by an English speaker saying, figure 1 shows figure 1 illustrates the magnetization process. Okay? And because of that, some people thought, mostly Japanese authors, thought that such a curve, it's called magnetization process. And if you go to a Japanese Physical Society meeting, people will say, draw a curve like this one say, jikakate instead of jikakyokusen. But it came from this wrong English. So at least in English, don't write magnetization process. Okay? This is magnetization curve in which magnetization is shown as a function of magnetic field. All right? So I told you about Japanese, German English, and also Japanese English in magnetism.